93 million miles away, the surface of our Sun is churning with energies we can barely comprehend. Beneath those roiling layers of plasma, magnetic field lines are twisting, stretching, building tension like coiled springs waiting to snap. And when they do snap, when those fields reconnect in a process that takes mere minutes, the Sun releases more energy than 1 billion hydrogen bombs detonating simultaneously. For most of human history, we saw the Sun as constant, unchanging, a reliable disk of light that rose and set with perfect regularity. We were wrong. The Sun is violent, it's explosive, and every so often, it unleashes catastrophic bursts of radiation and particles that cross the void of space and slam into our planet's magnetic field with forces that can cripple our technological civilization. On September 1, 1859, telegraph operators across Europe and North America watched sparks fly from their equipment. Papers caught fire, some operators reported receiving shocks through their hands. The sky itself glowed red and green so intensely that people in the Caribbean could read newspapers by the light of auroras normally confined to polar regions. This was the Carrington Event, the most powerful solar storm ever recorded, caused by a solar flare that modern analysis suggests released approximately 10 to the 32nd power ergs of energy, a number so vast it defies intuitive understanding. To grasp what this means, consider that the atomic bomb dropped on Hiroshima released roughly 6 times 10 to the 23rd ergs. A single major solar flare can release energies 10 billion times greater. Not 10 times, not 1,000 times, 10 billion times. This isn't just large, it's operating on a completely different scale of physical reality than anything we experience on Earth. The mechanics behind this violence remained mysterious until the mid-20th century, when scientists began understanding magnetic reconnection, a process where the Sun's twisted magnetic field lines snap and reconfigure, converting magnetic energy into kinetic energy, heat, and radiation with extraordinary efficiency. Dr. Eugene Parker, whose pioneering work in the 1950s laid the groundwork for modern solar physics, recognized that the Sun's magnetic field wasn't a static structure but a dynamic, constantly evolving system capable of storing and releasing enormous amounts of energy. What makes solar flares particularly remarkable isn't just their raw power, it's the speed at which this energy gets released. The entire process, from initial reconnection to peak energy output, can occur in just 10 to 20 minutes. Imagine compressing the explosive yield of 1 billion thermonuclear weapons into a time frame shorter than your lunch break. The power output during these brief windows can exceed the Sun's normal energy output by factors of 10 or more across specific wavelengths. Tonight, we're going to explore why this happens, how scientists have deciphered the physics behind these cosmic explosions, and what these eruptions reveal about the fundamental processes powering our star. We'll examine the historical events that first alerted humanity to solar violence, investigate the magnetic gymnastics that trigger flare eruptions, and understand why a single reconnection event can release energy equivalent to detonating every nuclear weapon on Earth thousands of times over, all while occurring in a volume of space that, by solar standards, is remarkably small. Before we begin this journey into solar physics, if you're fascinated by the extreme physics governing our Sun and the energetic processes that shape our solar system, subscribe and hit the thumbs up button. And here's a question: if you could witness one astronomical event in person from a safe distance, what would it be? Comment below, I'll pin the most creative answer. We often take the Sun for granted. It rises, it sets, it provides the warmth and light that make life possible. But understanding what happens when those magnetic field lines snap and reconnect, understanding why such a localized event can release energies that dwarf our most powerful weapons, requires diving into plasma physics, magnetohydrodynamics, and energy scales that challenge our everyday intuitions about power and violence. The Sun produces these flares regularly. Small ones happen multiple times per day. Medium-sized flares occur several times per week. And the truly massive events, the X-class flares that can disrupt satellite communications and power grids, happen several times per solar cycle, an 11-year period of rising and falling solar activity. We're not talking about rare cosmic accidents. We're discussing a fundamental aspect of how our star operates, a regular feature of stellar physics that happens to operate at energy scales we find almost incomprehensible. What happens in the Sun's corona during a major flare isn't just an explosion, it's a reorganization of magnetic topology, a fundamental restructuring of field line geometry that releases energy stored over days or weeks in magnetic form. The plasma involved reaches temperatures exceeding 10 million Kelvin, hot enough that atoms are completely ionized, and radiation across the electromagnetic spectrum, from radio waves to gamma rays, floods outward at the speed of light. Now let's begin our exploration of solar flare physics, starting with the structure of the Sun itself and the magnetic dynamo that makes these explosive events possible. Solar architecture. The Sun isn't a simple ball of burning gas, despite how it appears to our eyes. It's a layered structure, each zone governed by different physical processes, with the innermost core producing energy through nuclear fusion, and outer layers transporting that energy through radiation, convection, and eventually violent magnetic activity. Understanding solar flares requires understanding this architecture. Because the explosive events we observe happen specifically in the outer layers where magnetic fields dominate the physics. At the Sun's core, temperatures reach 15 million Kelvin and pressures exceed 250 billion atmospheres. Under these extreme conditions, hydrogen nuclei fuse into helium, releasing energy in the form of gamma rays through a process called the proton-proton chain. Each second, the Sun converts approximately 600 million tons of hydrogen into helium, releasing energy equivalent to 90 billion megatons of TNT. This happens continuously reliably, powering the star's luminosity with remarkable consistency. The energy generated in the core doesn't immediately escape. It spends hundreds of thousands of years bouncing through the radiative zone, a region where photons are constantly absorbed and re-emitted by the dense plasma, slowly working their way outward. Each photon travels mere millimeters before interacting with another particle, creating a random walk that takes immense time to traverse even modest distances. By the time energy from the core reaches the outer convective zone, it's been transformed from high-energy gamma rays into lower-energy photons across the electromagnetic spectrum. The convective zone begins about 200,000 kilometers below the Sun's visible surface. Here, the plasma becomes cool enough and opaque enough that radiation alone can't efficiently transport energy outward. Instead, hot plasma rises in massive convective cells, cools as it approaches the surface, and sinks back down to be reheated. This churning motion is visible as granulation on the Sun's surface, a constantly shifting pattern of bright cells surrounded by darker boundaries where cooler plasma descends. This convection does more than transport heat. It generates magnetic fields through a process called the solar dynamo. The rotating, electrically conductive plasma acts like a massive electrical generator, creating and amplifying magnetic fields that rise through the convection zone toward the surface. The Sun's differential rotation, the equator, rotates faster than the poles, stretches and twists these fields, amplifying them and creating the complex magnetic structures that eventually produce solar flares. Above the convective zone lies the photosphere, the visible surface of the Sun, where temperatures drop to about 5800 Kelvin. This is the layer we actually see when we look at the Sun, the source of most visible light. But the photosphere isn't where the action happens for solar flares. The real drama occurs higher up, in the chromosphere and corona. The chromosphere is a thin layer, just a few thousand kilometers thick, sitting immediately above the photosphere. Temperatures here behave counterintuitively. Instead of continuing to cool as you move away from the heat source, the chromosphere actually begins heating up, reaching temperatures around 20,000 Kelvin. This temperature reversal puzzled scientists for decades and relates directly to the energy transport mechanisms that also drive solar flares. Above the chromosphere lies the corona, the Sun's outermost atmosphere, and the primary theater for solar flare activity. Here, temperatures soar to over 1,000,000 Kelvin, despite being much farther from the fusion core. The corona is tenuous, its density is billions of times lower than Earth's atmosphere at sea level, but its extreme temperature means the particles within it possess enormous kinetic energy. The heating mechanisms driving coronal temperatures remain an active area of research, but magnetic energy clearly plays a central role. Magnetic field lines emerge from the photosphere and arch through the chromosphere into the corona, creating elegant loops and complex structures visible in extreme ultraviolet and X-ray images. These aren't static features. The photosphere's continuous motion, driven by convection below, constantly pushes and pulls on the magnetic field lines, braiding them, twisting them, and injecting magnetic energy into the corona. Think of the Sun's magnetic field like rubber bands connecting the surface to the outer atmosphere. As the surface churns and rotates at different speeds depending on latitude, those rubber bands get twisted tighter and tighter. The field lines accumulate stress, storing magnetic energy in their topology, the three-dimensional arrangement of how they loop and connect across space. This energy accumulation happens over days or weeks. Regions called active regions, visible as dark sunspots on the photosphere, mark areas where especially strong magnetic fields have emerged from below. These regions are cooler than their surroundings because the magnetic fields inhibit convective heat transport, but they're also sites of intense magnetic complexity. Multiple magnetic flux tubes emerge, interact, and create the tangled field configurations that eventually trigger flares. The magnetic field strength in active regions can exceed 3,000 Gauss, thousands of times stronger than Earth's magnetic field. These fields contain tremendous energy that doesn't dissipate easily in the corona's tenuous plasma. Instead, it accumulates, building potential energy in the magnetic configuration like water behind a dam. Scientists measure this accumulated energy by analyzing the topology of coronal magnetic fields, often using observations from spacecraft like NASA's Solar Dynamics Observatory, launched in 2010. SDO images the Sun continuously across multiple wavelengths, revealing the complex dance of plasma tracing magnetic field lines. By tracking how these structures evolve, researchers can estimate the magnetic energy stored in active regions and assess the likelihood of eruption. When field lines become twisted enough, when the magnetic stress reaches a critical threshold, the configuration becomes unstable. The field seeks a lower energy state, and the mechanism it uses to get there is magnetic reconnection, the fundamental process underlying every solar flare. But reconnection doesn't happen automatically. It requires specific conditions, particular geometric arrangements of field lines, and often a trigger that pushes an already stressed magnetic configuration past its tipping point. The photosphere, chromosphere, and corona form a coupled system. Energy generated by fusion in the core, transported through radiation and convection, ultimately gets stored in magnetic form in the corona. And when that stored energy releases, when reconnection occurs and magnetic energy converts to kinetic energy, heat, and radiation, the results are spectacular. Plasma accelerates to significant fractions of light speed. Temperatures spike to tens of millions of Kelvin, and radiation floods across the electromagnetic spectrum with intensity that can be detected 93 million miles away on Earth. This architectural understanding, the layered structure of the Sun, the dynamo generating magnetic fields, the convective motions twisting those fields, and the corona storing magnetic energy, provides the foundation for understanding why solar flares are so energetic. The Sun isn't just large, it's a fusion reactor wrapped in a magnetic field generator, topped with an atmosphere where energy stored in invisible field lines can release in minutes, producing explosions visible across the solar system. Magnetic reconnection. The physical mechanism that triggers solar flares, magnetic reconnection, represents one of the most important processes in plasma physics, relevant not just to solar activity, but to phenomena throughout the universe. Understanding reconnection means understanding how magnetic field lines, which in ideal plasma theory should remain frozen to the plasma and never break or merge, actually do break and reconfigure when conditions are right, releasing stored energy with extraordinary efficiency. In ordinary plasma, magnetic field lines are frozen in, a concept from magnetohydrodynamics describing how plasma and magnetic fields move together as if glued to each other. This frozen-in condition means that field lines maintain their identity and topology unless something disrupts the ideal behavior. For most of the Sun's atmosphere, this approximation holds reasonably well. Plasma motions drag field lines around, but the lines themselves don't break or merge. Magnetic reconnection occurs when this frozen-in condition breaks down in localized regions. When oppositely directed field lines are pushed together, forced into close proximity by plasma motions, a thin current sheet forms at the boundary between them. In this sheet, the frozen-in approximation fails. The field lines can diffuse through the plasma, break their connections, and reconnect in a new configuration with lower magnetic energy. Dr. Peter Sweet and Dr. Eugene Parker developed the first theoretical models of reconnection in the 1950s, recognizing that magnetic energy could convert to kinetic energy and heat through this process. Their models, however, predicted reconnection rates too slow to explain observed solar flares. The energy release happened too quickly, minutes instead of hours, suggesting the real reconnection process was more efficient than early theories predicted. The breakthrough came with the Petschek model in 1964, which showed that reconnection could occur much faster if standing shock waves formed in the outflow region, heating and accelerating plasma away from the reconnection site. This model better matched observational timescales and became the foundation for understanding explosive reconnection events. Modern understanding recognizes that reconnection involves several key elements. First, there's the diffusion region where field lines actually break and reconnect. This region is extremely small, often just a few hundred kilometers across in solar flares, tiny compared to the overall scale of active regions spanning tens of thousands of kilometers. Second, there are the outflow regions where newly reconnected field lines rapidly contract like released rubber bands, accelerating plasma to velocities exceeding 1,000 kilometers per second. The energy budget during reconnection is staggering. Before reconnection, magnetic energy is stored in the stressed field configuration. A typical active region might contain 10 to the 32nd ergs or more of magnetic energy accumulated over days as photospheric motions twist and shear the coronal fields. When reconnection triggers, this energy doesn't disappear, it converts to other forms. Approximately half the released energy goes into kinetic energy, accelerating plasma particles. Electrons and ions gain enormous speeds, with electrons reaching near relativistic velocities in the most powerful events. This acceleration happens through several mechanisms: direct electric fields in the reconnection region, shock acceleration in the outflow zones, and turbulent acceleration in the churning plasma surrounding the reconnection site. The other half of the energy goes into heating. Temperatures in the reconnection region and immediate surroundings spike to 10, 20, sometimes 30 million Kelvin, temperatures where thermal X-rays dominate the radiation output. This superheated plasma radiates intensely, producing the brilliant X-ray emissions that spacecraft like GOES satellites detect and classify to determine flare magnitude. Solar flares are classified by their X-ray brightness in the 1/8 angstrom wavelength band. C-class flares are weak, producing X-ray flux levels around 10 to the -6 watts per square meter at Earth's orbit. M-class flares are medium strength, 10 times more powerful. X-class flares are the strongest, exceeding 10 to the -4 watts per square meter and capable of causing widespread disruptions to satellite communications and high-frequency radio propagation. But even X-class designation underestimates the most powerful events. The largest flare measured in modern times occurred on November 4, 2003, an X-28 flare that saturated detectors. Subsequent analysis suggested the flare likely reached X-45 or higher, releasing energy exceeding 6 times 10 to the 32nd ergs over the course of about 11 minutes. To put this in perspective, humanity's total energy consumption for an entire year is roughly 5 times 10 to the 20th ergs. This single solar flare released more than 1 trillion years of human civilization's annual energy use. The geometry of reconnection determines where and how energy releases. The simplest configuration involves anti-parallel field lines pointing in opposite directions that meet and reconnect. More complex geometries involve sheared or twisted fields, where reconnection proceeds in 3 dimensions, rather than the idealized 2-dimensional models. These 3D reconnection events can be more explosive because they involve larger volumes of stressed magnetic field. Observations from missions like Hinode, launched by JAXA in 2006, reveal the intricate structure of pre-flare magnetic configurations. Hinode's solar optical telescope can resolve features as small as 120 kilometers on the Sun's surface, revealing the fine-scale structure of active regions. What looked like simple magnetic loops in earlier observations turned out to be bundles of smaller structures, each capable of contributing to the total energy released during reconnection. The trigger for reconnection often involves emerging magnetic flux, new magnetic field rising from below the photosphere and interacting with existing coronal fields. As new flux emerges, it pushes and distorts the overlying field, creating current sheets and sheared boundaries where reconnection can initiate. Alternatively, photospheric motions can slowly build stress until the field becomes unstable, triggering a cascade of reconnection events. Once reconnection begins, it doesn't necessarily stop immediately. In many flares, the process is impulsive and repetitive. Initial reconnection might trigger further instabilities, leading to multiple reconnection episodes over minutes or hours. These appear in observations as multiple peaks in X-ray emission, each representing a fresh burst of energy release as additional magnetic flux reconnects. The efficiency of magnetic reconnection in converting stored energy to kinetic energy and heat approaches 50% in many solar flares, remarkably high for any energy conversion process. For comparison, even the most sophisticated human-engineered systems rarely exceed 40% efficiency in converting potential energy to useful work. The Sun's magnetic reconnection achieves this through plasma physics operating at scales and energies we cannot replicate in laboratories. Particle acceleration during reconnection produces not just thermal plasma, but also energetic particles with velocities approaching the speed of light. These particles, primarily protons and electrons, stream away from the Sun, traveling along magnetic field lines or escaping into interplanetary space. When they strike Earth's magnetosphere, they can penetrate to high latitudes and pose radiation hazards to satellites and astronauts. The reconnection process itself is mediated by collisions and wave-particle interactions at microscopic scales. In the diffusion region, where field lines break, plasma instabilities and turbulence allow the frozen-in condition to fail. Researchers studying these microscopic processes use spacecraft like NASA's Magnetospheric Multiscale mission, which investigates reconnection in Earth's magnetosphere at scales down to electron motion, providing insights applicable to solar reconnection events. Understanding magnetic reconnection isn't just academic. Predicting when reconnection will trigger in a given active region remains one of the central challenges in space weather forecasting. Magnetic fields can remain stressed for days without erupting, and then suddenly release their energy in minutes. The difference between a stable configuration and an explosive one often involves subtle changes in field topology or the emergence of new flux that tips the balance toward instability. Energy scales. Comparing solar flare. Energies to human-scale explosions helps contextualize the numbers, but even these comparisons barely convey the true magnitude of the energy involved. When we say a major solar flare releases energy equivalent to 1 billion hydrogen bombs, we're not exaggerating for effect. We're actually understating the violence because the comparison doesn't capture the speed, the efficiency, or the multi-wavelength nature of the energy release. A modern thermonuclear weapon, one of the most powerful devices humanity has created, releases energy through nuclear fusion, the same process powering the sun's core. A typical strategic warhead might yield 1 megaton, equivalent to 1 million tons of TNT, or about 4 times 10 to the 22nd ergs. The most powerful weapon ever detonated, the Soviet Tsar bomber tested in 1961, yielded 50 megatons, or roughly 2 times 10 to 24th ergs. Now consider a major X-class solar flare releasing 10 to the 32nd ergs. To match this with Tsar bomber explosions, you'd need 50 million of them detonating simultaneously. Stack them differently. You'd need every nuclear weapon in every arsenal on Earth, approximately 13,000 warheads, detonated together, and then repeat that simultaneous detonation 3,800 times to approach the energy of a single large solar flare. The energy density makes the comparison even more striking. Nuclear weapons release their energy in volumes measured in cubic meters. Solar flares release comparable total energy in volumes measured in cubic kilometers, regions of the corona spanning 10,000 to 100,000 kilometers in each dimension. The energy fills enormous volumes of space, yet the density remains high enough to heat plasma to tens of millions of Kelvin and accelerate particles to relativistic speeds. Temporal concentration intensifies the violence. A nuclear detonation releases most of its energy in microseconds to milliseconds. A major solar flare reaches peak energy output in 10 to 20 minutes. This sounds slower, but consider the total energy involved. The power output, energy per unit time, during peak flare activity can exceed 10 to the 30th ergs per second, or 10 to the 30th watts. The sun's total luminosity is about 4 times 10 to the 33rd ergs per second. During major flares, localized regions of the corona are producing significant fractions of the entire sun's normal power output. To appreciate this power level, consider that all human civilization uses roughly 2 times 10 to the 20th ergs per second of power. The sun produces 20 trillion times more continuously from fusion. A major solar flare from a region smaller than the sun's total surface by a factor of several thousand temporarily produces power outputs comparable to the fusion core's total production. It's as if a tiny fraction of the sun's surface suddenly decided to compete with the entire star's energy output, and succeeded. The energy doesn't release uniformly across all wavelengths. Solar flares produce characteristic emissions across the electromagnetic spectrum, each wavelength providing information about different physical processes. Soft X-rays, wavelengths of 110 angstroms, come primarily from thermal plasma heated to 1030 million Kelvin. Hard X-rays, wavelengths shorter than 1 angstrom, and gamma rays indicate non-thermal processes, energetic electrons colliding with chromospheric plasma and producing Bremsstrahlung radiation. Extreme ultraviolet radiation increases dramatically during flares, with emissions in the 94 angstrom and 131 angstrom bands, wavelengths produced by highly ionized iron increasing by factors of 10 to 100. This EUV radiation doesn't reach Earth's surface because our atmosphere absorbs it, but it significantly affects the upper atmosphere, heating and expanding the thermosphere, and increasing atmospheric drag on satellites in low Earth orbit. Radio emissions from solar flares span frequencies from tens of kilohertz to tens of gigahertz. Type 2 and Type 3 radio bursts produced by energetic electrons streaming through the corona and exciting plasma waves provide diagnostic information about particle acceleration and coronal conditions. Some flares produce radio emissions so intense that they overwhelm satellite communication signals, causing temporary blackouts in affected frequency bands. The Carrington Event of September 1, 1859, provides historical context for extreme solar activity before the space age. Richard Carrington and Richard Hodgson independently observed a white light flare on the Sun, visible even without specialized filters because of its extraordinary brightness. 17 hours later, a coronal mass ejection associated with the flare struck Earth's magnetosphere, compressing it and driving the most intense geomagnetic storm in recorded history. Telegraph systems worldwide experienced disruptions. Operators disconnected batteries and found their systems still operational, powered entirely by currents induced in the long telegraph wires by the rapidly changing magnetic field. Some operators reported shocks, papers caught fire from sparks, and the auroras, normally confined to high latitudes, appeared as far south as Cuba and Hawaii, lighting up the night sky with red and green curtains visible to the naked eye. Estimating the Carrington Event's energy remains challenging because we lack direct measurements from that era. Modern analysis of geomagnetic disturbances recorded by ground-based magnetometers suggests the flare itself released energy in the range of 10 to the 32nd to 10 to the 33rd ergs, making it one of the most powerful events in recorded history. The associated coronal mass ejection carried additional energy in the form of kinetic energy and magnetic fields, bringing the total energy budget even higher. For comparison, consider natural disasters on Earth. The largest earthquake recorded, the 1960 Valdivia earthquake in Chile, released approximately 2 times 10 to the 25th ergs, equivalent to about 50,000 megatons. Devastating, certainly, but still 7 orders of magnitude less than a major solar flare. The eruption of Mount Tambora in 1815, the largest volcanic eruption in recorded history, released roughly 10 to the 26th ergs. Impressive by terrestrial standards, utterly dwarfed by solar flares. Even cosmic impacts pale in comparison. The asteroid or comet impact that ended the Cretaceous period 66 million years ago, killing the dinosaurs and reshaping Earth's biosphere, released energy estimated at 4 times 10 to the 30th ergs, approaching but still not quite matching the largest solar flares. And that impact represented a singular catastrophic event accumulated over the object's entire journey through space. Solar flares represent regular, repeating events that the Sun produces through its normal magnetic activity. The Sun releases this energy not through fusion, the core continues fusion regardless of surface magnetic activity, but through magnetic reconnection, converting energy stored in field topology to kinetic energy and radiation. This means the energy source is fundamentally different from nuclear weapons or volcanic eruptions or asteroid impacts. It's the energy of twisted space, of magnetic fields stressed into configurations that nature finds untenable and must release. Quantifying energy in solar flares requires integrating emissions across all wavelengths and accounting for energy in particle acceleration, plasma heating, and kinetic motion of erupted material. Researchers combine observations from multiple spacecraft, GOES satellites measuring X-rays, SDO observing extreme ultraviolet emissions, RESI detecting gamma rays and hard X-rays, radio telescopes tracking radio bursts, to construct comprehensive energy budgets. Recent large flares provide benchmarks. The X-17 flare of October 28, 2003 released approximately 3 times 10 to the 32nd ergs. The X9 flare of August 9, 2011 released about 8 times 10 to the 31st ergs. These events, among the most powerful of the past 2 decades, demonstrate that X-class flares routinely achieve energies equivalent to hundreds of millions to billions of thermonuclear weapons, and they're not even the theoretical maximum the Sun can produce. The theoretical upper limit for solar flare energy remains uncertain, but estimates suggest the Sun could potentially produce superflares, releasing 10 to the 34th ergs or more, energy levels observed on other Sun-like stars but not yet definitively detected on our Sun. Such an event would release energy equivalent to 50 billion Tsar bomber detonations, an explosion so vast it would represent one of the most violent localized events possible in stellar physics, short of core collapse supernovae or neutron star collisions. Historical record. Humanity's awareness of solar violence developed slowly, pieced together from scattered observations, unexplained technological failures, and eventually systematic scientific investigation. The Sun appeared constant for most of human history, a reliable source of light and warmth that varied only with the seasons. Recognizing its capacity for explosive violence required first developing technologies sensitive enough to detect the effects, then building the scientific framework to understand the underlying physics. Key sunspots provided the earliest evidence of solar variability. Chinese astronomers recorded sunspot observations as early as 165 BCE, noting dark blemishes visible on the Sun's surface during hazy conditions or at sunrise and sunset. European astronomers, using the newly invented telescope in the early 1600s, systematically observed and documented sunspots with Galileo Galilei, Christoph Scheiner, and Thomas Harriot, all making detailed observations between 1610 and 1612. These observations revealed that sunspots weren't fixed features. They appeared, evolved, and disappeared over days to weeks. They moved across the Sun's surface, revealing the star's rotation. But the connection between sunspots and solar eruptions remained unknown for centuries because the effects of solar flares, radiation and particle emissions couldn't be detected without specialized instruments. The first hints of solar influence on Earth came from magnetic observations. In 1724, George Graham noticed unexplained fluctuations in compass needles, variations that couldn't be explained by local magnetic sources. Anders Celsius and Olof Hjorta made similar observations in Sweden in the 1740s, correlating magnetic disturbances with aurora sightings and suggesting a connection between auroras and magnetic variations. The breakthrough linking solar activity to terrestrial effects came during the Carrington Event. On September 1, 1859, Richard Carrington was projecting an image of the Sun onto a screen in his private observatory in England, sketching sunspot groups, when suddenly 2 bright patches of white light appeared in the sunspot complex. The brightening lasted about 5 minutes before fading. Carrington recognized he was witnessing something extraordinary and immediately recorded the observation. Independently, Richard Hodgson in London observed the same phenomenon from his telescope, confirming Carrington's observations. Neither astronomer knew what they'd witnessed. It would be decades before the physics of solar flares became understood, but Carrington suspected a connection to the intense magnetic storm that struck Earth 17 hours later. The telegraph system, newly expanded across Europe and North America, provided unprecedented evidence of the storm's power. Telegraph operators reported sparks, shocks, and fires. Some disconnected their battery power supplies and found their systems still functional, driven by currents induced in the long telegraph wires by Earth's rapidly changing magnetic field. In Washington, D.C., the telegraph superintendent sent and received messages to Portland, Maine, for 2 hours using only the auroral current with no battery power. The magnetic disturbance was global. Magnetometer readings from observatories worldwide showed the most extreme deviations ever recorded, with some instruments going off scale. The auroras extended to tropical latitudes, visible in Cuba, Jamaica, Panama, and Hawaii. Gold miners in the Rocky Mountains reportedly woke up at 1 a.m. thinking dawn had arrived because the sky glowed so brightly. Estimating the Carrington Event's magnitude remains challenging. because modern flare classification didn't exist in 1859. No X-ray detectors, no satellite observations, no spectroscopic measurements. Researchers reconstruct the event's intensity by analyzing the geomagnetic disturbance it produced using ice core and tree ring data showing isotope anomalies from enhanced cosmic ray production during the storm. The consensus suggests the Carrington flare was X40 or stronger, potentially the most powerful flare in the past 500 years. If a Carrington-scale event struck Earth today, the consequences would be catastrophic for technological civilization. The 2008 National Academy of Sciences report, Severe Space Weather Events: Understanding Societal and Economic Impacts, estimated that a Carrington-class storm could cause $1 to $2 trillion in damage to infrastructure and require years for complete recovery. Another significant historical event occurred in February 1872, less than 13 years after Carrington. Another intense white light flare produced a geomagnetic storm of similar magnitude, though less well documented because it coincided with the Great Chicago Fire Recovery period and received less public attention. Telegraph disruptions again occurred worldwide and auroras appeared at equatorial latitudes. The early 20th century brought systematic sunspot observation and the recognition of the 11-year solar cycle. George Ellery Hale's observations in 1908 using the newly developed spectroheliograph revealed that sunspots possessed strong magnetic fields, the first direct evidence linking solar magnetism to surface features. Hale showed that sunspot pairs had opposite magnetic polarities and that these polarities reversed with each 11-year cycle, suggesting an underlying 22-year magnetic cycle. Radio observations opened new windows into solar activity. In 1942, British radar operators noticed intense interference during daytime hours. James Hay investigated and determined the interference originated from the sun, the first detection of solar radio emissions. This discovery launched radio astronomy and provided a new tool for studying solar flares, which produce characteristic radio bursts across a wide frequency range. The space age revolutionized solar observation. Satellites above Earth's atmosphere could observe ultraviolet and X-ray emissions absorbed by the atmosphere, revealing the full spectrum of solar radiation and allowing direct flare detection. The orbiting solar observatory satellites, launched between 1962 and 1975, provided the first systematic X-ray observations of solar flares, establishing the classification system still used today. OSO-5, launched in 1969, carried X-ray detectors, the Carrington X20 flare, on August 4, 1972, part of a spectacular active region that produced multiple major flares and several coronal mass ejections. 1 CME from this active region struck Earth while Apollo 16 astronauts were in space, fortunately after their return from the lunar surface, and another occurred between the Apollo 16 and Apollo 17 missions. Had the timing been different, astronauts on the Moon could have received lethal radiation doses. The Halloween storms of October-November 2003 provided the space age's most dramatic demonstration of solar violence. Active Region 486, one of the largest sunspot groups in decades, produced 17 major flares in just 12 days, including the X28, likely X45 flare, on November 4th. These eruptions spawned numerous coronal mass ejections that battered Earth's magnetosphere, causing widespread satellite anomalies, communication disruptions, and transformer damage in power grids. Sweden's power grid experienced a 50-minute blackout. South African power systems suffered transformer damage. Airlines rerouted polar flights to lower latitudes to avoid radiation exposure. The Japanese Adios 2 satellite, a critical Earth observation platform, suffered permanent damage to its solar panels and failed shortly afterward. Estimates suggest the economic impact exceeded several $100 million from satellite losses alone, not counting broader infrastructure effects. The Japanese GOES satellite recorded the November 4th flare's X-ray output until the detectors saturated. The radio emissions were so intense that they jammed satellite communications and GPS signals, creating navigation errors of tens of meters. Auroras appeared as far south as Texas and Florida, and scientists realized that had the CMEs been slightly faster and more Earth-directed, the geomagnetic storm could have approached Carrington Event levels. Historical observations reveal that extreme solar events occur more frequently than intuition suggests. Ice core data showing beryllium-10 and carbon-14 isotope variations created when cosmic rays strike Earth's atmosphere and enhanced during magnetic storms provide a 10,000-year record of solar activity. This record shows several events comparable to or exceeding the Carrington event within the past millennium. The Miyake event of 774-775 CE, identified through tree ring analysis showing a massive carbon-14 spike, likely represents a solar energetic particle event significantly more powerful than any observed in the modern era. The fluence of high-energy particles must have been extraordinary to create the observed isotope anomaly. While not necessarily a larger flare than Carrington, the associated particle event was clearly exceptional. These historical events demonstrate that solar violence isn't rare. The Sun regularly produces energetic flares and CMEs capable of affecting Earth. We've been fortunate that the largest modern events haven't been perfectly geo-effective, directly aimed at Earth with optimal magnetic field orientation to maximize coupling with the magnetosphere. But history shows such events are inevitable on timescales of decades to centuries. Plasma dynamics. The physics governing solar flares operates in the plasma state, the fourth state of matter, where temperatures are high enough that electrons separate from atomic nuclei, creating a gas of charged particles governed by electromagnetic forces as much as thermal pressure. Understanding plasma behavior is essential to understanding how magnetic reconnection can release such enormous energies in such short time frames. In ordinary gases, particles interact primarily through collisions and pressure gradients. In plasmas, especially the tenuous, hot plasmas in the solar corona, electromagnetic forces dominate. Charged particles spiral along magnetic field lines constrained by the Lorentz force to follow helical paths around the field. This coupling between plasma and magnetic field creates the magnetohydrodynamic regime, where plasma and field move together, frozen to each other in ideal circumstances. The corona's plasma has peculiar properties. Its density is extraordinarily low, roughly 10 to the 9th particles per cubic centimeter in quiet regions, compared to 10 to the 19th particles per cubic centimeter in Earth's atmosphere at sea level. Despite this low density, the temperature exceeds 1 million Kelvin, giving particles average speeds of hundreds of kilometers per second. The combination of high temperature and low density means the corona barely exerts pressure despite its extreme heat. This tenuous plasma can store enormous magnetic energy because the magnetic pressure exceeds the plasma pressure by factors of 10 to 100 in active regions. The magnetic field doesn't just passively respond to plasma motion, it actively constrains and shapes the plasma distribution. Field lines act like elastic bands under tension, storing energy in their geometry and topology. When field lines are twisted or sheared, free magnetic energy accumulates. This free energy represents the difference between the current field configuration and the lowest energy potential field configuration, the state the field would adopt if it could relax completely. The greater the free energy, the more unstable the configuration becomes, and the more energy is available for release during reconnection. The reconnection process itself involves breaking the frozen-in condition through localized regions where resistivity becomes important. In the thin current sheet forming where oppositely directed field lines meet, the frozen-in approximation fails. Various mechanisms can provide the necessary resistivity. collisions in slightly denser regions, turbulent mixing, or wave particle interactions that effectively scatter particles and allow field lines to diffuse through the plasma. Once reconnection begins, the physics becomes explosive. Field lines snap and reconfigure, releasing magnetic tension like released springs. The newly reconnected field lines contract rapidly, accelerating plasma in the outflow regions. This acceleration can reach 0.01 to 0.1 times the speed of light for electrons, velocities where relativistic effects become measurable, and radiation produces gamma rays through inverse Compton, scattering, and nuclear interactions. The energetic particles accelerated during reconnection don't all escape into space. Many spiral along field lines and impact the chromosphere below the reconnection site, where the plasma is denser. These impacts produce Bremsstrahlung radiation, hard X-rays and gamma rays created when energetic electrons decelerate rapidly in the dense chromospheric plasma. Observations of hard X-ray footpoints marking where energetic particle beams strike the chromosphere provide crucial diagnostic information about particle acceleration in the corona above. Temperatures in the reconnection region reach 10 to 30 million Kelvin, creating superheated plasma that radiates intensely in soft X-rays. The thermal emission spectrum, characterized by continuum radiation and emission lines from highly ionized atoms, reveals the plasma's temperature, density, and composition. Ion atoms stripped of 15 to 24 electrons produce characteristic emission lines in the extreme ultraviolet and X-ray portions of the spectrum, serving as thermometers for coronal plasma. The Ramati High Energy Solar Spectroscopic Imager, or RHESI, launched in 2002, revolutionized observations of high-energy processes in flares. By imaging hard X-rays and gamma rays with arc-minute resolution, RHESI revealed the spatial structure of particle acceleration regions and the detailed spectral evolution during flares. Observations showed that particle acceleration begins within seconds of reconnection onset and can continue for many minutes as reconnection proceeds. Plasma instabilities play crucial roles in triggering and sustaining reconnection. The tearing mode instability, for example, can spontaneously fragment a current sheet into multiple smaller reconnection sites, a process called fractal or turbulent reconnection. This fragmentation can dramatically increase the reconnection rate by creating multiple pathways for magnetic energy release rather than a single, slow diffusion region. The plasma beta, the ratio of plasma pressure to magnetic pressure, determines which forces dominate in different coronal regions. In the low corona above active regions, beta is typically much less than 1, meaning magnetic forces completely dominate over thermal pressure. The plasma is essentially a slave to the magnetic field, tracing field lines and responding to magnetic stresses rather than expanding freely under its own pressure. Higher in the corona, beta gradually increases as a magnetic field strength decreases and plasma pressure becomes more significant. The transition occurs around 1 to 2 solar radii above the surface, where magnetic and plasma pressures become comparable. Above this transition, plasma can more freely expand, and the solar wind, a continuous outflow of coronal plasma, begins to dominate the dynamics. Solar flares occur below this transition region, in the low beta corona, where magnetic forces dominate. The stored magnetic energy can efficiently convert to kinetic energy and heat because the plasma doesn't have sufficient pressure to resist the magnetic forces. The field configuration determines the plasma distribution, and when that configuration changes through reconnection, the plasma responds violently to the sudden release of magnetic stress. Modeling these plasma dynamics requires solving the magneto-hydrodynamic equations, a coupled set of partial differential equations describing how plasma and magnetic fields evolve together. These equations, derived from Maxwell's equations combined with fluid dynamics, describe the conservation of mass, momentum, and energy in magnetized plasma. Solving them for realistic solar conditions requires supercomputers and sophisticated numerical methods. Modern simulations can now model entire active regions, following the evolution of magnetic fields emerging from below the photosphere, their interaction with overlying coronal fields, the buildup of magnetic stress, and eventually the reconnection that triggers flares. These simulations reproduce many observed features: twisted field lines, current sheet formation, bidirectional outflows from reconnection sites, and the acceleration of particles to high energies. The Interface Region Imaging Spectrograph, or IRIS, launched in 2013, provides unprecedented observations of the chromosphere and transition region, the thin layer between the chromosphere and corona, where temperature rises from 10,000 to 1,000 Kelvin over just a few hundred kilometers. IRIS observations reveal that this region is far from static. Small-scale jets, rapid heating events, and waves constantly transport energy from below into the corona, contributing to coronal heating and potentially to the energy budget of solar flares. Understanding plasma dynamics in the solar atmosphere remains an active research frontier. Questions persist about the exact mechanisms heating the corona to millions of Kelvin, about how magnetic energy is efficiently converted to particle kinetic energy during reconnection, and about the role of turbulence and small-scale instabilities in mediating large-scale energy release. Each new mission, each higher-resolution observation, reveals additional complexity and richness in the plasma physics governing our star. The plasma itself is not uniform. Active regions contain loops, arcades, and helmet streamers, complex magnetic structures filled with plasma at varying densities and temperatures. Plasma confined in closed magnetic loops can reach temperatures exceeding 5 million Kelvin, visible in extreme ultraviolet images as bright loops arching above the photosphere. When these loops become unstable and reconnect, the confined plasma suddenly finds itself on open field lines, free to stream away into interplanetary space, carrying energy and momentum from the flare site. The sheer volume of plasma involved in major flares is staggering. A large flare might involve 10 to the 12th kilograms of plasma, about 1 trillion metric tons, heated to tens of millions of Kelvin and accelerated to thousands of kilometers per second. This mass, though enormous by terrestrial standards, represents just a tiny fraction of the Sun's total mass, yet it carries energy comparable to billions of thermonuclear explosions. Particle acceleration. Among the most remarkable aspects of solar flares is their ability to accelerate particles, electrons, protons, and heavier ions, to energies approaching the speed of light within seconds. This acceleration produces radiation across the electromagnetic spectrum, creates hazardous radiation environments in space, and provides insights into fundamental plasma physics processes operating throughout the universe. The particle acceleration mechanisms in solar flares remain incompletely understood despite decades of research. Multiple processes likely contribute, with their relative importance varying depending on flare geometry, magnetic field strength, and plasma conditions. The challenge is that acceleration must occur rapidly, producing relativistic particles in seconds, and efficiently, converting a significant fraction of available magnetic energy into particle kinetic energy. Direct electric field acceleration in the reconnection region represents one mechanism. In the diffusion region, where field lines break and reconnect, the frozen-in condition fails, allowing electric fields parallel to the magnetic field to develop. These parallel electric fields can directly accelerate charged particles, increasing their energy as they traverse the reconnection region. Electrons, being lighter, respond more readily to these fields and can achieve relativistic speeds, significant fractions of light speed, within the compact reconnection zone. Shock acceleration provides another mechanism. When reconnection occurs, fast-mode magnetohydrodynamic shocks form in the outflow regions, traveling outward from the reconnection site at speeds exceeding the local Alfvén speed, the characteristic wave speed in magnetized plasma. Particles crossing these shocks can gain energy through a process called first-order Fermi acceleration, repeatedly bouncing between converging plasma flows and gaining energy with each crossing. Stochastic acceleration through turbulence offers a third mechanism. The reconnection region and surrounding plasma are turbulent, filled with magnetic fluctuations and plasma waves at various scales. Particles interacting with this turbulent electromagnetic environment undergo random scattering, gaining or losing energy with each interaction. On average, in converging flows and compressing magnetic fields, particles gain energy, a second-order Fermi process that, while slower than shock acceleration, can operate over larger volumes and longer timescales. Observations reveal that electrons accelerate to energies of tens of keV to hundreds of MeV during major flares. These energetic electrons produce hard X-ray and gamma-ray emissions through two mechanisms: Bremsstrahlung radiation, when they collide with ambient plasma in the chromosphere, and inverse Compton scattering when they interact with photons from the Sun. Risi observations show that hard X-ray sources appear in the chromosphere as distinct footpoints where energetic electron beams impact dense plasma, and as coronal sources where electrons emit while still in the acceleration region. Protons and heavier ions also accelerate during flares, though typically to lower velocities than electrons due to their greater mass. Protons can reach energies of tens to hundreds of MeV, and in the largest events, GeV energies, comparable to particles accelerated in human-built particle accelerators. These energetic protons produce gamma rays through nuclear interactions when they collide with ambient atoms in the chromosphere, exciting nuclei and producing characteristic gamma-ray lines. The gamma-ray observations from flares provide direct evidence for nuclear interactions. The 2.223 MeV line from neutron capture, the 0.511 MeV positron annihilation line, and de-excitation lines from carbon, nitrogen, and oxygen nuclei all appear in gamma-ray spectra from major flares. These emissions confirm that protons reach energies of tens of MeV, sufficient to induce nuclear reactions in the solar atmosphere. Solar energetic particle events, when accelerated particles escape the Sun and stream through interplanetary space, pose significant hazards for spacecraft and astronauts. The January 20, 2005 solar proton event, associated with an X7 flare, produced proton fluxes at Earth exceeding 5,000 particles per square centimeter per second per steradian for energies above 10 MeV. Such fluxes can penetrate spacecraft shielding, damage electronics through single event upsets, and deliver radiation doses dangerous to human tissue. The August 1972 event, occurring between the Apollo 16 and Apollo 17 missions, delivered radiation doses that would have been life-threatening to astronauts in spacesuits on the lunar surface. Estimates suggest an unshielded astronaut would have received 200 to 400 rem, well into the range causing acute radiation sickness. Had the timing been different, this event could have turned a lunar mission into a catastrophe. Particles accelerated during flares don't all escape into space. Many remain trapped in closed magnetic loops, bouncing between mirror points where strengthening magnetic fields reflect them back toward the loop apex. These trapped particles continue to emit radiation, producing sustained hard X-ray and microwave emissions that can last minutes to hours after the initial acceleration phase. The energy spectrum of accelerated particles, the distribution of particle numbers as a function of energy, typically follows a power law. The number of particles decreases as energy increases, with more particles at low energies and progressively fewer at higher energies. The spectral index describing this power law varies between flares, indicating differences in acceleration efficiency or conditions in the acceleration region. Understanding the spectral evolution during flares provides clues about acceleration mechanisms. In some flares, the hard X-ray spectrum hardens, becomes richer in higher energy photons as the flare progresses, suggesting that acceleration becomes more efficient or extends to higher energies over time. In others, the spectrum softens, indicating that acceleration weakens or that higher energy particles escape or lose energy more rapidly than they're being accelerated. The total energy in accelerated particles can represent a significant fraction, 10 to 50%, of the total energy released during a flare. In a flare releasing 10 to the 32nd ergs, this means 10 to the 31st to 5 times 10 to the 31st ergs goes into accelerating particles, for electrons accelerated to 50 keV, a typical energy in flare X-ray observations. This corresponds to accelerating roughly 10 to the 37th electrons, an enormous number that nevertheless represents only a tiny fraction of the electrons in the flare volume. The magnetic field topology determines where particles can travel. Closed magnetic loops confine particles, forcing them to bounce between footpoints. Open field lines allow particles to escape into interplanetary space, becoming solar energetic particles that can reach Earth and other planets. The configuration determines whether a flare produces dangerous particle radiation at Earth or whether the particles escape in other directions, missing our planet. Heliospheric images on stereo spacecraft launched in 2006 provide stereoscopic views of the Sun and can track energetic particle events as they propagate through interplanetary space. These observations reveal that particle acceleration occurs not only in the initial flare but continues as shock waves driven by coronal mass ejections propagate outward. Particles can undergo additional acceleration as they interact with these traveling shocks, gaining energy hundreds of times over minutes to hours. The composition of accelerated particles provides additional clues about acceleration mechanisms. Some elements, particularly our heavier ions, show enhanced abundances in solar energetic particle events compared to their solar abundances. These enhancements suggest that acceleration preferentially affects certain species, possibly due to differences in charge-to-mass ratios or how different ions respond to wave-particle interactions in the turbulent acceleration region. Relativistic electrons produce radio emissions through electron-cyclotron maser emission and plasma emission as they spiral in magnetic fields and interact with plasma waves. Radio observations at frequencies from tens of kilohertz to gigahertz reveal distinct burst types. Type 2 bursts from shock accelerated electrons, type bursts from electron beams streaming along open field lines, type 4 bursts from trapped electrons in closed loops. Each burst type provides diagnostic information about where and how particles are accelerating. The energetic particles themselves can drive instabilities in the ambient plasma, generating waves that scatter and thermalize lower energy particles. This creates feedback between particle acceleration and the plasma environment, with accelerated particles modifying the conditions that affect subsequent acceleration. Modeling these coupled processes requires sophisticated kinetic plasma simulations that track individual particle trajectories in evolving electromagnetic fields. Modern missions like Parker Solar Probe, launched in 2018, provide in situ measurements of solar energetic particles much closer to the Sun than previous spacecraft. Approaching to within 10 solar radii of the Sun's surface, Parker can sample particle populations shortly after they're accelerated, before interplanetary transport modifies their distributions. These measurements will help constrain acceleration mechanisms by providing observations closer to the source regions. The ultimate goal is predicting not just whether a flare will produce energetic particles, but what energy spectrum they'll have and where they'll propagate. This requires understanding the magnetic connection between the flare site and Earth, the efficiency of different acceleration mechanisms for given flare properties, and how particles scatter and propagate through the turbulent interplanetary magnetic field. These remain open questions in space physics with significant practical implications for protecting astronauts and technology. Coronal mass ejections. Solar flares rarely occur in isolation. Most major flares accompany coronal mass ejections, vast clouds of magnetized plasma expelled from the Sun's atmosphere, carrying billions of tons of material into interplanetary space at speeds reaching thousands of kilometers per second. The relationship between flares and CMEs and the mechanisms driving these massive eruptions represent crucial aspects of solar physics with profound space weather implications. Coronal mass ejections involve much more mass than flares. While flares primarily involve energy release, radiation, and accelerated particles, CMEs physically eject material. A large CME can contain 10 to the 12th to 10 to the 13th kilograms of plasma, 10 billion to 100 billion metric tons, along with embedded magnetic fields carried along with the plasma. This mass streams outward, initially accelerating through the lower corona before coasting through interplanetary space. The magnetic structure of CMEs typically takes the form of a flux rope, a twisted, helical magnetic configuration that looks like a spring or coil. This structure forms in the corona before eruption, created by the same photospheric motions that stress coronal magnetic fields and set up conditions for flares. The flux rope contains stored magnetic energy and helicity, a measure of how twisted and interlinked the magnetic field is, that gets transported into interplanetary space during the eruption. CME initiation mechanisms remain debated, but most models invoke magnetic instabilities that overcome forces confining plasma in the corona. The torus instability occurs when the overlying magnetic field constraining a flux rope becomes too weak compared to the rope's internal magnetic pressure. The rope expands, and the expansion further weakens the overlying field in a runaway process, leading to eruption. Alternatively, catastrophic loss of equilibrium can occur when the coronal magnetic field can no longer support a stable configuration, triggering sudden eruption. The energy budget for CMEs involves both the kinetic energy of the erupting mass and the magnetic energy in the ejected flux rope. For a CME with mass 10 to the 13th kilograms traveling at 1,000 kilometers per second, the kinetic energy alone is approximately 5 times 10 to the 31st ergs, comparable to a large solar flare. The magnetic energy can be comparable or larger, bringing the total energy budget to 10 to the 32nd ergs or more for the most powerful events. The relationship between flares and CMEs is complex. Most large CMEs accompany major flares, but small flares can occur without CMEs, and some CMEs occur with only minor or no detectable flares. The current understanding suggests they're different manifestations of the same underlying process, magnetic reconnection and eruption, but occurring in different magnetic configurations. Some field geometries favor large-scale eruption, CMEs, others favor localized energy release, confined flares, and some produce both. The white light coronagraphs on SOHO, the Solar and Heliospheric Observatory, launched in 1995, revolutionized CME observations by providing continuous monitoring of the corona from space. SOHO's LASCO coronagraphs can detect CMEs as they erupt from the Sun, tracking their evolution as they expand through the field of view. These observations revealed that CMEs occur much more frequently than ground-based observations suggested, several per day during solar maximum and roughly one every few days even during solar minimum. Fast CMEs traveling faster than the solar wind they're moving through drive shock waves ahead of them. These CME-driven shocks can accelerate particles to high energies through the same shock acceleration mechanisms operating in flare sites. The September 2005 event, for example, produced a shock that accelerated protons to energies exceeding 1 GeV, creating a radiation storm that lasted several days and required astronauts on the International Space Station to shelter in more heavily shielded areas. When a CME strikes Earth's magnetosphere, the interaction depends critically on the CME's magnetic field orientation. If the CME's magnetic field points southward, opposite to Earth's northward pointing field, reconnection occurs on the dayside magnetopause, allowing solar wind energy to penetrate Earth's magnetic shield. This drives geomagnetic storms, compresses the magnetosphere on the dayside, stretches it on the night side, and injects energetic particles into the radiation belts. The Halloween storms of 2003 demonstrated the power of fast, magnetically unfavorable CMEs. Multiple CMEs from the same active region struck Earth in quick succession, each contributing to the geomagnetic disturbance. The cumulative effect pushed the DST index, a measure of geomagnetic storm intensity, below 400 NT, indicating an extreme storm. Power grids experienced induced currents exceeding 100 amperes in some transformer neutrals. Transformers in South Africa failed, and satellite anomalies numbered in the dozens. The March 1989 geomagnetic storm, caused by a CME from an X-15 flare, demonstrated that even events smaller than the Carrington Event can cause significant damage. The storm induced currents in Quebec's power grid that tripped circuit breakers and caused a cascading failure, leaving 6 million people without power for up to 9 hours in the middle of winter. Transformers at multiple locations suffered permanent damage from saturation and overheating caused by geomagnetically induced currents. CME propagation through interplanetary space involves complex interactions with the ambient solar wind. Fast CMEs plow through slower solar wind, creating shock waves and compressed sheaths of plasma ahead of the erupting flux rope. These shock sheaths often contain turbulent magnetic fields and can be more geo-effective than the CME itself if their magnetic field orientation is favorable for reconnection with Earth's magnetosphere. The transit time from Sun to Earth depends on CME speed. Typical CMEs travel at 300–500 kilometers per second, taking 3 to 4 days to reach Earth. Fast CMEs exceeding 1/500 km/s can arrive in less than 24 hours, leaving little time for preparation. The fastest CME on record from the August 1972 event traveled at approximately 2,150 kilometers and reached Earth in just 14.6 hours, one of the shortest transit times ever observed. Stereo spacecraft provide multi-viewpoint observations of CMEs, allowing three-dimensional reconstruction of their structure and trajectory. With 2 spacecraft orbiting the Sun at different positions, one ahead of Earth, one behind, Stereo can observe CMEs from multiple angles, determining whether they're Earth-directed or headed elsewhere in the solar system. This capability significantly improves space weather forecasting by removing ambiguity about CME direction that single viewpoint observations suffer from. The magnetic cloud structure within many CMEs represents the erupted flux rope, characterized by strong, smoothly rotating magnetic fields, low plasma temperature compared to ambient solar wind, and low plasma beta indicating magnetic forces dominate. These magnetic clouds can maintain their coherent structure across tens of millions of kilometers, eventually reaching and affecting not just Earth but Mars, Jupiter, and even spacecraft in the outer solar system. CMEs interact with each other in interplanetary space. When a fast CME overtakes a slower one, they can merge, creating complex magnetic structures. The July 2012 event, which narrowly missed Earth, involved multiple CMEs that interacted and merged, creating an extremely powerful composite structure. Analysis suggested that had this event struck Earth, it could have produced a geomagnetic storm comparable to or exceeding the Carrington Event. The kinetic energy in fast CMEs can modify the heliospheric structure over vast distances. The CME-driven shockwaves accelerate particles that propagate throughout the inner heliosphere, producing ground-level enhancements. Rare events where energetic protons penetrate Earth's atmosphere and are detected by neutron monitors on the ground. Only about 70 ground-level enhancements have been observed since monitoring began in the 1940s, occurring exclusively during the most extreme solar particle events. The magnetic flux transported by CMEs represents a significant fraction of the active region's total flux. As flux ropes erupt, they carry magnetic helicity, a topological property quantifying how twisted and linked field lines are out of the corona. This helicity removal may be necessary for the long-term evolution of solar magnetic fields, providing a mechanism for the Sun to shed complex magnetic structures that build up through the differential rotation and convection, continuously tangling surface fields. Understanding CME formation and evolution remains crucial for space weather forecasting. Current models can predict CME arrival time at Earth with uncertainties of approximately +T7 hours for fast events, useful for raising alerts but insufficient for precise operational decisions. The magnetic field orientation within the CME, critical for determining geo-effectiveness, can only be measured reliably by spacecraft in situ at Earth's orbit, providing at most an hour of warning before the CME's impact on the magnetosphere. Future missions aim to improve forecasting by providing observations from locations between the Sun and Earth. The proposed Lagrange mission would station spacecraft at the L5 Lagrange point, 60 degrees ahead of Earth in its orbit, providing a side view of Earth-directed CMEs and potentially improving prediction of both arrival time and magnetic field orientation. Combined with machine learning approaches analyzing large databases of CME observations, these advances may significantly improve our ability to predict space weather impacts. Technological vulnerability. Our modern technological civilization possesses unprecedented capabilities, but also unprecedented vulnerabilities to solar activity. The same infrastructure enabling global communication, navigation, and power distribution creates pathways through which solar flares and coronal mass ejections can disrupt or damage critical systems. Understanding these vulnerabilities requires examining how electromagnetic radiation and energetic particles interact with technology, both on Earth's surface and in space. Solar flares produce intense bursts of electromagnetic radiation across the spectrum, reaching Earth at light speed 8 minutes after eruption. The X-rays and extreme ultraviolet radiation don't penetrate the atmosphere, absorbed in the thermosphere and ionosphere, but they dramatically affect those atmospheric layers. The thermosphere heats and expands during major flares, increasing atmospheric drag on satellites in low Earth orbit by factors of 2 to 10. This enhanced drag affects thousands of satellites, from the International Space Station at 400 kilometers altitude to small CubeSats and debris objects throughout the low Earth orbit environment. Satellites must compensate by using onboard propulsion to maintain altitude, consuming propellant and shortening mission lifetimes. During the Halloween storms of 2003, atmospheric expansion was so severe that satellite operators temporarily lost track of hundreds of objects, requiring weeks to recatalogue the space environment. The ionosphere, a layer of ionized plasma in the upper atmosphere, responds dramatically to flare radiation. The sudden increase in ionizing radiation creates additional free electrons, altering the ionosphere's density and structure. These changes affect radio wave propagation, particularly high-frequency communications that rely on ionospheric reflection to bounce signals over the horizon. Major flares cause shortwave radio blackouts lasting minutes to hours, affecting aviation communication, maritime operations, and amateur radio. GPS signals traversing the ionosphere twice, once on the way down from satellites, once on the way back after ground reflection, experience delays that depend on electron density along the signal path. The ionospheric disturbances during major flares create rapid density variations, producing navigation errors that can exceed 10 meters, unacceptable for precision applications like aircraft landing systems or surveying. The December 6, 2006 X9 flare disrupted GPS across the entire sunlit hemisphere for approximately 30 minutes. Solar energetic particles arriving at Earth hours to days after flares pose direct hazards to satellites through several mechanisms. High-energy protons can penetrate spacecraft shielding and deposit charge in electronic components, causing single-event upsets, bit flips in computer memory, or logic circuits. A single proton striking a critical component at the wrong moment can crash a satellite computer, requiring ground intervention to reboot and reconfigure the spacecraft. More severe single event effects include latch-up, where a proton strike creates a high current path through a semiconductor device, potentially destroying the component if power isn't quickly removed, and burnout, where permanent damage occurs from the energy deposition. The EDIOS-2 satellite failure during the Halloween storms likely resulted from solar panel damage caused by energetic protons degrading the solar cell material and electrical connections. Radiation dose accumulation represents a long-term hazard. Satellites carry total ionizing dose budgets, the amount of cumulative radiation exposure their components can withstand before performance degrades unacceptably. Major solar particle events can deliver a significant fraction of this dose in days or hours, effectively aging satellite components by months or years. Mission planners must account for both average dose rates and worst-case event doses when designing spacecraft and estimating lifetimes. Astronauts face biological radiation risks during solar particle events. The August 1972 event, had it caught Apollo astronauts on the lunar surface, would have delivered doses potentially exceeding 400 rem to skin and 100 rem to blood-forming organs, levels causing acute radiation sickness. Current space station operations include radiation monitoring and protocols for crew to shelter in more heavily shielded areas during severe events, but Mars missions, with transit times of months through deep space, will face significant challenges from unpredictable solar particle events. Geomagnetic storms driven by CME impacts affect Earth's surface infrastructure through geomagnetically induced currents. When the magnetosphere responds violently to a CME impact, the rapidly changing magnetic field creates fluctuating currents in the ionosphere and magnetosphere. These fluctuating currents, in turn, induce electric fields at Earth's surface through electromagnetic induction, driving currents through any long conductors, particularly power transmission lines and pipelines. Power transformers are especially vulnerable to geomagnetically induced currents. Transformers are designed to operate with alternating current at 50 or 60 Hz, but GICs introduce quasi-DC currents that can saturate the transformer core, dramatically increasing losses and overheating the windings. During severe storms, GIC amplitudes can exceed 100 amperes, far above the transformer's DC tolerance. The March 1989 Quebec blackout resulted from GIC-induced transformer trips and the subsequent cascading failure as the grid attempted to reroute power. The vulnerability extends beyond individual transformers to grid-level effects. Modern power grids interconnect regions and balance generation and load across wide areas. This interconnection improves efficiency and reliability under normal conditions, but creates pathways for disturbances to propagate during geomagnetic storms. A single failed transformer can trigger protective relays that isolate sections of the grid, potentially leading to cascading failures across wider regions. Estimating potential damage from a Carrington-class event today produces sobering numbers. The 2008 National Academy of Sciences report suggested direct economic costs of $1–2 trillion from damaged transformers, blackouts lasting weeks to months in severely affected regions, and indirect costs from interrupted economic activity. Recovery could require years because large high-voltage transformers are custom-built with lead times of 12 to 20 months and limited global manufacturing capacity. Pipeline systems face corrosion risks from GICs. The induced currents flowing through pipelines drive electrochemical reactions at the pipe surface that accelerate corrosion. While this effect doesn't cause immediate failure, accumulated damage over multiple geomagnetic storms can weaken pipes and lead to eventual leaks. Pipeline operators must monitor and account for GIC-induced corrosion in maintenance planning. Undersea communication cables, while less susceptible to GICs than power lines due to shorter, straight line distances and different grounding arrangements, still experience storm-induced effects. The February 2022 Starlink satellite loss attributed to a geomagnetic storm that increased atmospheric drag and caused 40 newly deployed satellites to deorbit, demonstrated that even moderate space weather events can impact commercial space operations, with losses estimated at approximately $50 million. Aviation faces multiple space weather hazards. Radiation exposure at cruising altitudes increases during solar particle events, particularly on polar routes where Earth's magnetic field provides less shielding. Airlines monitor space weather forecasts and can reroute polar flights to lower latitudes when necessary, adding flight time and fuel costs. Communication blackouts during flares can force aircraft to use alternative frequencies or satellite communications, adding complexity to air traffic control. The economic integration and just-in-time supply chains of modern civilization amplify space weather impacts. Losing GPS navigation affects shipping, trucking, and aviation. Communication disruptions affect financial markets. Power outages ripple through supply chains. The interconnected nature of infrastructure means failures in one sector cascade into others. A 2017 study estimated that a severe space weather event's total economic impact, including indirect costs, could approach $10 trillion globally. Mitigation strategies exist but face economic and technical challenges. Power grid operators can install blocking devices to prevent GICs from entering transformers, but this requires capital investment with no immediate return. Satellite designers can add radiation shielding and fault-tolerant computing, but these increase mass and cost. Space weather forecasting can provide warning, but forecasts currently lack the precision needed for confident operational decisions. The challenge is that severe space weather events are low-probability, high-consequence scenarios. The Carrington Event occurred 165 years ago. Statistical analysis of historical data suggests the probability of a Carrington-class event in any given decade is roughly 10%, non-negligible but not imminent enough to drive immediate investment in extensive protective measures. This creates a classic risk management dilemma: how much to invest in protection against rare but potentially catastrophic events. Recent policy initiatives have begun addressing space weather risks. The United States released a national space weather strategy in 2019, outlining coordinated approaches across government agencies to improve forecasting, harden infrastructure, and develop response capabilities. The ProSwift Act, passed in 2020, requires more comprehensive monitoring and research, but implementation remains incomplete, and many critical infrastructure operators continue to view space weather as a secondary concern compared to more immediate operational challenges.